object has moved, the distance an object has moved from the origin. So the origin is just a start position. Any start position is going to be marked as 0, kind of on our timeline. Distance an object has moved from the origin over a period of time. So like I said, we're on a timeline, time measured in using the variable t. Okay, we're going to do our other terms first, and then we're going to work through the relationship part. So our next term is velocity. Velocity is kind of a fancy word for speed, but it's a little bit different. Velocity is the rate of change of displacement, the rate of change of displacement with respect to time. Okay, so we have displacement, it's just a measurement of the distance traveled. Then we have velocity, which is the rate of change of displacement. So really the speed at which you are displacing something. Okay, and again, as soon as we see this, the rate of change, we're thinking, oh, that has to do with slope, which is related to derivatives. So that's where we get into derivatives here. Next term, acceleration. Acceleration is the rate of change of velocity. Okay, so the rate of change of velocity. Again, with respect to time. All right, so what do we have here? We have a rate of change, and then we have a rate of change of a rate of change. If a rate of change is a derivative, then the rate of change of a rate of change is the derivative of a derivative. So we're taking second derivatives today. So how are we going to do this? Well, we're given a relationship within the definition. So displacement is going to be measured as s with respect to t. So these functions, this is our original function. We're going to be modeling the motion of an object in a straight line given by the function s of t. Okay? Now, velocity then is s prime of t. Okay? The new function that we create, because the derivative of any function is another function, is v of t, velocity with respect to time. Okay, so v of t is the first derivative of the displacement function. Acceleration is the second derivative of the displacement function. So s double prime with respect to t, s double prime of t. And that is acceleration with respect to time. It is also the first derivative of v of t. Okay, so acceleration is the first derivative of the velocity function. It's the second derivative of the displacement function. Good so far?
Yep.
Displacement, how do we measure distance? What are some measurements that we use for just distance, change in distance?
Meters.
Meters. Okay, so the easiest one that we use is meters. Velocity has some options. What's some typical units of velocity? A measurement of speed, you could say. It's not exactly speed, but
meters a second.
Meters per second would be the most common when we're talking about scientific modelings. If you're in a car, it's kilometers per hour, but it could also be measured in meters per second. Acceleration then, if it's the second derivative of displacement, Do you guys know what acceleration is measured as? Acceleration due to gravity? Meters per second squared. All right, this is our information for today. This is what we're going to try to understand, and we're going to try to do it algebraically by taking derivatives and creating those derivative functions, and also graphically. We're going to see how the graphs relate to each other. One final note is just the difference between speed and velocity. So this chart is done. Boom. Why do we use the word velocity? Well, speed is a scalar quantity. Scalar quantity. What does that mean? It does not describe direction. Does not describe direction. So if you give someone a speed, it's always measured in positive values. Speed can only be positive. It does not tell you the direction, whether you go left or right or up or down. At 10 kilometers an hour, all you can say is 10 kilometers per hour. It doesn't tell you the direction. So always positive. Velocity, however, is a vector quantity. It describes magnitude and direction. Positive or negative values to indicate direction. Okay, so speed only describes magnitude. Speed only describes how fast you're going. It doesn't tell you which direction you're going. Vectors, a velocity is a vector quantity. It describes how fast you're going and which direction you're moving in. And again, we're talking about linear motion. So you're either moving forward or you're moving backward. Those are the two options, positive or negative from that starting point. Okay, which is right here, the origin in our displacement definition. All right, example 1 is dealing with first and second derivatives. We are going to determine f double prime of 2 for the function f of x equals 1/3 x cubed minus x squared minus 3x plus 4. Okay, so what are we doing? There's a few steps here if we want to think through it. We're given the function f of x. We're going to find its first derivative, then we're going to find the second derivative, then we're going to find the value of the second derivative at 2. So here we go. Finding the first derivative, f prime of x. 3 times 1/3 is 1, so I have x squared minus 2x minus 3. We're good with that? It's not too fast. Second derivative. That's just taking the derivative of the first derivative. 2x minus 2. Next step. Sub in 2 everywhere we see x. So now we have f double prime of 2. It's 2 times 2 minus 2, which is 2. Hopefully all the 2's aren't confusing. That wasn't super difficult. Why don't we skip? No, we'll keep going how we're going. That's it. So if we wanted to sketch this thing, maybe let's just talk about what it actually means. So what did we find out? Well, if f of x tells us the displacement of an object with respect to time, and f prime of x tells us the speed or velocity of that object with respect to time. Is it moving forward or backward? Is it moving fast or slow? Then f double prime tells us how fast it's accelerating. So is it moving faster and faster with respect to time, or is it moving slower and slower at certain points on the curve? So what we found out is that when, let's say we translated this into, distance and time, then we found out that after 2 seconds, it's accelerating at a rate of 2 meters per second. Okay, so it is moving forward and it is accelerating at a rate of 2 meters per second. And actually, it's moving backwards. But example 2. We have a construction worker. He accidentally drops a hammer. From 90 meters high while working on the roof of a new apartment building. The height of the hammer, S, measured in meters, after t seconds is modeled by 90, so it's starting height, minus 4.9 t squared. And the restrictions on this is that t is always greater than 0. Okay, so a real world problem, time measured from the drop, time must be greater than 0. Also right here, negative 4.9 t squared, that is acceleration due to gravity on Earth minus wind resistance. If there was no wind resistance, if you were in a vacuum, then you'd have negative 4.9 meters per second squared would be your acceleration due to gravity. All right, what do we need to do? We need to do a couple things. We're going to do we're going to determine the average velocity. Average velocity between 1 second and 4 seconds. So let's do that. The average velocity, that's kind of going back to the slope of a secant line, an estimation of velocity. And this average velocity is the change in s over the change in time. Okay, so this is kind of like, well, it's the slope of a secant line is basically what it is. So we're finding the point in the numerator. We are taking our velocity, or sorry, our distance, our height, when x is 4, when t is 4 seconds, and then subtracting the difference at when it's 1 second. So all we do is we sub it in s of 4 minus s of 1 over the change in time, which is 4 minus 1.
Wait, but is it a function for velocity or for how much it falls?
So this is the function of height that's given.
Okay, but you want the average velocity, so you should have the prime.
Right, so velocity is the rate of change of height. Does that make sense?
Yeah, I see.
So we're taking the height at the 2 points and dividing by the change in time to get the average.
Yeah.
Okay, I'm going to work just to the right for one more step. So this is basically just taking our function s of t and subbing in 4 for t. So we've got 90 minus 4.9 times 4 squared, and then subtracting 90 minus 4.9 times 1 squared over 3. I'm not going to do all this in my head, but we could click it into our calculator. We would end up with negative 73.5 over 3, which is negative 24.5. Statement, therefore, the average rate, the average velocity. So we would say average rate of change of height, but the rate of change of height is velocity. So the average velocity is, or between 1s and 4s, is negative 24.5 meters per second. So again, that's velocity, which is kind of like speed. What does the sign indicate? What does the negative sign indicate in this problem?
It's falling down.
It's moving down. Yeah, hammer is moving down. Be a bit more mysterious if it were moving up. C says, determine the velocity of the hammer at 1 second and at 4 seconds. Determine velocity. Again, I'm going to underline velocity just so that we're aware that we're talking about first derivative here. Determine velocity at 1s and at 4s. So to determine the velocity, we are taking the derivative of our height function, of our displacement function. Okay, so just a note, since v of t is equal to the first derivative of the displacement function, we need to first take that. So we're taking the derivative of 90 minus 4.9 t squared. The derivative of that is this first constant becomes 0. Then I have 2 times negative 4.9, which is 9.8, negative 9.8 t. Okay, so now we have a function for velocity. All we need to do then is find the velocity at 1, which is negative 9.8 times 1. So 1 second after he drops it, the velocity of the falling hammer is negative 9.8 meters per second. And the velocity at 4 seconds is negative 9.8 times 4, which is negative 39.2 meters per second. So you can see how our average velocity falls somewhere in between there. It's a pretty good estimate of that whole span, and yet there is a pretty great difference between the speed or the velocity at 1 second and the speed or the velocity at 4 seconds. Good, both of them are negative, so they indicate that it's continuously moving down. This hammer continues to move down, and it's moving down at an increasing velocity, okay? Or increasing magnitude, I guess I should say. Increasing magnitude. Okay, when will the hammer hit the ground? When will the hammer hit the ground? I'm going to erase what I have here so far. I'm going to go back to the top. And I'm just going to indicate that we have already taken the derivative of this guy. And it was negative 9.8 t. And then D says, when will hammer hit ground? The hammer will hit the ground when the displacement, so if we think about our building here where he dropped the hammer from, speeding up, speeding up, speeding up, and how far has it traveled by the time it's hit the ground?
90 meters.
90 meters. Okay, so the displacement will be 90 meters once it hits the ground. So from here, when you're still on the roof with your hammer, displacement is 0. It hasn't moved from its original position. Once it's moved 90 meters, it will hit the ground and be done moving. Okay? displacement, sorry, let's think about that backwards. Let's think about the ground as the origin, and it's starting at a displacement of 90, and it's going to reach a displacement of 0. Yes? Sorry. Displacement will be 0 at ground level. That's more helpful. So we need to solve S of t equals 0.
Wouldn't be S of t plus 90 equals 0?
Okay, so we've got 90 minus 4.9 t squared equals 0. Again, I'm taking our displacement, so the distance that it is from the ground. It's starting at a height of 90, and it is accelerating down toward the ground until it hits 0. So we can add 90 to both sides. Sorry, subtract 90 from both sides, and then divide both sides by negative 4.9. That's going to give us positive 90 over 4.9. And this we can do in our calculator, but we end up with 90 over 4.9 is 18.37 approximately. And that is still t squared. So in order to find the time that it takes to hit the ground, we need to take the square root of that, which results in 2 possible answers, because the square root can be positive or negative. And that happens at plus or minus 4.29 seconds. One of these answers we can reject, because we know that t is greater than or equal to 0. So since t is greater than or equal to 0, t equals 4.29, or approximately 4.3 seconds to hit, or for hammer to reach ground. E, part E, we've got 2 more parts, E and F. E says determine the impact velocity. Impact velocity. So, translation. What is the velocity when the hammer hits the ground? Essentially, yeah, so essentially how hard does the hammer hit the ground? And all we need to do then is take our time of impact and sub it into our velocity function v of t. So we're looking for the v of 4.3, the velocity at 4.3 seconds. That's negative 9.8 times 4.3. Punch that in. You should get negative 42.14, and that is measured in meters per second. That's pretty quick. 42 meters per second straight down into the ground. And part F. Part F says determine the acceleration function. Acceleration function. The acceleration function is the derivative of the velocity function. Acceleration is the derivative of the velocity, so A of t is equal to v prime of t, which is the derivative of negative 9.8 t, which is negative 9.8.
So the acceleration now is always 9.8.
So yes, we want to make some notes. Therefore, acceleration is constant at negative 9.8 meters per second squared. And this is, again, the acceleration due to gravity for any falling object on Earth if we ignore air resistance. Okay, brief notes. Slowing or speeding up? When velocity and acceleration have the same sign, object is being pushed in the direction it is traveling. So if velocity and acceleration have the same sign, it's already going a direction and it's being pushed that direction, speeding up. When velocity, I'm just going to write the opposite thing, when velocity and acceleration have opposite signs, when velocity and acceleration have opposite signs, object is being pushed in the opposite direction of travel, then it would be slowing down. Okay, so whether it's positive or negative doesn't matter. It's how the signs relate to each other. Translation on this. Speeding up is if v of t times a of t is positive, is greater than 0. Slowing down is if you take the value of the function, velocity function, at a particular time, and you multiply it by the value of the function, the acceleration function, at a particular time. That would be negative. They're fighting against each other. It's a positive times a negative or a negative times a positive. Then it's slowing down. Okay, for the third example, I have this printed graph for you. The story that goes with it. The position of a particle moving along a straight line, so we're talking about linear motion, is represented by the function. You can name the function. It's s with respect to t equals t cubed minus 12t squared plus 36t, where distance s is measured in meters and time t is measured in seconds, and t is greater than or equal to 0. You can see that because we're starting at the origin and moving only to the right. Okay, the graph of the position function, that's the one that's given. This displacement function or position function is this cubic function that was given. And we need to sketch the graph of the velocity and acceleration functions. So in order to do that, we're going to analyze the graph that has been given already. I'm going to zoom in. Okay, we're going to need a ruler to follow along. We're going to sketch the graph of the velocity function in our second one, and then the acceleration function in our next one, just by analyzing this curve. So what can we gather about the linear motion of this particle just by looking at the graph that is given? What's true about its motion?
This is its velocity, or
This is its displacement.
displacement. Okay.
So it's starting at a specific point, and then over time, what is it doing?
Well, it moves away kind of slow.
Yeah, it moves away, and generally speaking, it moves away, and then it
And then it returns.
returns,
And then it moves again.
and then it goes away again. Okay, so it's moving sometimes forward, sometimes backward. What else?
I'm really new to these terms.
Is it always moving the same speed?
No, it starts moving fast and then it slows down.
Yeah.
And then it goes in reverse.
Good. So it's fast here, and then it's slowing, and then slowly going backwards, and then speeding up, going backwards, and then slowing, and then going forward again. It's almost like you're running across the gym. You're slowing down to touch the wall and coming back the other way, and slowing down to touch the wall and going back the other way. And somehow you started at top speed. You got shot out of a cannon or something. Okay? Good enough? Good enough. That's talking about it. So what we're going to do then is find out where are we moving forward and where are we moving backward, because that's going to tell us a lot about the velocity. Well, if we kind of mark this spot right here, through this interval from 0 to 2, he's moving forward. We have a positive slope, okay? Positive slope. Positive slope. Then what? Well, then we have a negative slope all the way to t equals 6. So in this range, we have a negative slope. And then to the end, it keeps on going. We don't have an end to it because t is greater than 0. So where t is greater than or equal to, not greater than or equal to, where t is greater than 6, we have positive slope again. Okay, what we can do, so we've just indicated slope. The slope of our displacement is going to correspond to the positive and negative of our derivative function. These graphs don't line up exactly perfect. They're pretty close. So I'm going to pretend that they line up perfectly. What I'm going to do is I'm going to take a dotted line at t equals 2, and I'm going to bring it all the way down
It's marked on every
to my derivative. Yep. And I'm going to take our other change in direction at t equals 6 and take a dotted line and take it down to positive 6. All right, what does that indicate? Well, we just said that if this is going to be our derivative function, if this is going to be our function v with respect to t, okay, then it's going to indicate the slope of this, our original displacement graph. So where the slope of the original graph is positive, the value of the derivative is going to be positive. Okay? Where the slope of the displacement function is negative, the value of our velocity function is going to be negative. Okay? Now, how negative is it? Well, the value of the velocity function, the value is indicated over here on the vertical axis, correspond to the exact slope of the curve at the given point that they match up. So right here, where we have a change of direction, the slope is 0, right? Well, that means it's crossing through at 0. on our slope function or our velocity function. Same thing here. At t equals 6 in our displacement function, the slope is 0, so there must be a 0 on that curve. Also, the original curve is cubic, so the next curve must be quadratic. Another thing to talk about, we said that the slope, the velocity, was greatest at the beginning and then it slowed down. Well, that's right here. We have the highest velocity at the beginning, and then it, over time, slows down. And actually, I should put this y-intercept at about the right spot. It crosses around there, just so you have a fairly accurate depiction of the curve here. Good. So the original function, we can look at the slope to determine the sine, and sketch. We don't have exact values here, but we have sketch of our derivative function. Okay. Now we're going to do the same thing, because if this is a function in and of itself, which it is, then its derivative will represent the slope of this original function. So what do we know? Well, we know that on this function, right at the minimum point here, right at t equals 4, we have a change in direction from a negative slope to a positive slope. So what we're going to do is we're going to take that t equals 4, we're going to trace it down, and this, since now our next graph, which is a with respect to t, is the derivative of v of t, it represents the slope of v of t, we know that we're going to have a negative slope, okay, up until here, and then we're going to have a positive slope, okay, and the slope is changing, but it's changing at a constant rate, okay, so our next derivative is a linear function, and it crosses at about negative 24 if we want to try to be as accurate as possible. So it will look something like that. Okay, I'm going to talk about these two graphs that we drew very briefly and just write down what we said. So we have positive velocity between 0 and 2. So maybe over here, positive velocity from 0 to 2, and from t greater than 6, and we have negative velocity when t is between 2 and 6. That's our velocity curve. Now let's talk about acceleration briefly. We have positive acceleration when t is greater than 4. It's right here. And we have negative acceleration when t is less than 4. Okay, what we have also done kind of indirectly is we found the relationship between t equals 4 and our original displacement graph right here. You don't need to learn this a lot right now, but right there where t equals 4 is the apex. Okay, it's where acceleration changes. Negative acceleration to positive acceleration. Good, good. Okay, to wrap up example 3, we're going to look at the different intervals and what the slope is on the velocity graph and the acceleration graph, so we can see how they're interacting together. If they're working against the direction of motion, or if it's speeding up, if the force is working with the direction of motion. So chart. Intervals. What's v of t doing during that interval? What is a of t doing during that interval? And then what is the product of v of t, a of t? And we're just looking at the sign. Is it positive or is it negative? And then we're going to talk about it. Talk about the motion of the particle. And these probably need to be the biggest. I should have slid this thing over. And then description of slope. Our intervals are from 0 to 2, from 2 to 4, from 4 to 6, and from 6 to 8. 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. And this one crosses at 4. Good to go? Okay, so velocity, we're looking at v of t, which is up here, right? Is that in this interval, or nope, sorry, this is s of t. This is displacement. This is v of t. This is a of t. That gives it some more context. Good. From 0 to 2, is this positive or negative?
It's positive.
Positive. From 2 to 4.
Negative.
Negative. 4 to 6. Negative. 6 to 8.
Positive.
Positive. All right, looking at acceleration. From 0 to 2, it is
Positive.
over here.
Oh no, negative.
Negative. 2 to 4. Negative. 4 to 6. Positive. 6 to 8. Positive. So now we're just looking at how they are interacting with each other, how they work together or against each other. So from 0 to 2, the product of their signs is negative. What does that tell us? Well, we know that its velocity is forward. It's moving directionally forward because velocity is positive, but acceleration is negative. So this is moving forward and slowing down. All right, what about this one? If the product of the velocity and acceleration is positive, then that means it's being forced in the same direction that it's already going. It's being pushed in the same direction it's already going. So this is moving backward or moving in reverse, and it's speeding up. So anytime we have a positive in the product of the two signs, we're going to end up speeding up. Whether it's forward or backward will be determined by the velocity. Okay, so this is backward and speeding up, which means from 4 to 6 is also moving backward. We're moving in reverse. But this time acceleration is positive, so that means we're slowing down. And our last interval, velocity is positive, so the direction is positive. We're moving forward, and because the product of the two is also positive, it's being pushed the same direction that it's heading, which means it's speeding up. Okay, remember this is a particle moving in a straight line. And we can also talk about the slope. as it relates to the moving particle, as it relates to the functions v of t and a of t. So what does this mean here? If it's moving forward and slowing down, then what we have in the original function is a positive slope that is decreasing. So we have a positive slope that is decreasing. It's heading towards 0. So from 0 to 2, we have a positive slope that is decreasing. From 2 to 4, so from here to here, we have a negative slope that is decreasing. So its negativity is increasing, but the slope, since we're in negative land, negative numbers, it's decreasing. The value is decreasing. It's getting steeper and steeper and steeper. So here we have a negative and decreasing. From 4 to 6, it's still negative, but it's increasing. It's coming back to 0 before it heads back up. So we're negative and increasing. And our last interval from 6 to 8, we are positive and increasing. It's getting steeper and steeper and steeper as it moves up. Positive and increasing. Okay, we can do it even without looking back at the graph at this point, because we have the velocity and acceleration signs, and since these are both rate of changes, it tells us what the rate of change is going to be, and it tells us what the rate of change of the rate of change is going to be. So if the velocity is positive, we have a positive slope. If the acceleration is decreasing, then we have a slope that is decreasing. Same in the next interval. We have a velocity that's negative and acceleration that's negative, so we have a negative slope that is decreasing. Then we have a negative slope that is increasing, then we have a positive slope that is increasing. So we can get all that just from the signs of the derivative. Okay, in example 4, you're just given a picture of a position time graph. It is a motorcycle that is changing its position with respect to time. It's going further away from its start position and then coming back toward its start position. So maybe it's going to the store to get something and then coming home, or maybe it just drives around the block. Whatever it's doing, we're going to analyze it using a chart, and for each interval from 0 to A, from A to B, from B to C, etc., we're going to determine the sign of the velocity and the acceleration, just like we did in the previous example, just by looking at the slope of this graph this time. So we have another chart. Underneath, you can do it. You've got interval, the intervals. We're going to describe the slope. And from that slope, we're going to determine the velocity, the sign of the velocity, and the sign of acceleration formula. Okay, our intervals are from 0 to A, from A to B, B to C, C to D, D to E, and E to F. And we're going to use two descriptors for each interval, for the slope of each interval. It's going to be either increasing, positive or negative, and it's going to be either increasing or decreasing. So from 0 to A, positive or negative?
Positive and increasing.
Positive and increasing. Going to do it fairly quickly. I'm just going to write short forms of these words. Natasha, from A to B. Good. Jake, from B to C, positive or negative? The slope. So it's heading down. The slope, so the value of the function is positive, but the slope is negative because it's heading down, and it's heading down faster and faster, which means it's negative and decreasing. David, C to D.
It's negative and increasing.
Negative and increasing. Natasha, D to E.
Negative and increasing.
Yeah, I think on your picture is probably better than mine, but I think it's supposed to be 0.
Oh.
Is it horizontal on your picture? Looks pretty much, should be, yeah, okay. So we'll go slope equals 0. So there's no movement. It's perfectly horizontal. And then the last one there, from E to F, Jake, is the slope positive or negative? Is it heading up or down? Negative. And is it increasing or decreasing? Is it getting more negative, or is it going to turn and go positive?
Negative.
Yeah, it's decreasing. Negative and decreasing. Okay, so just like in the last example, but we're kind of flipping it over. Last example, we did these columns first, and then we described the slope. This time we've described the slope, and now from that we can get velocity and acceleration. So if we have a positive slope, then the velocity must be positive. And if the velocity is increasing, the slope is increasing, then they must be accelerating in the same direction that they're heading. It's positive, positive. Okay, from A to B, we determine that the slope is still positive, but this time the velocity, your speed, is decreasing. So the force, the acceleration, is working against the direction that you're heading. From B to C, we're now heading backward or in reverse. So our velocity is negative. And we're speeding up, so we're decreasing. Then we have negative and increasing, negative and positive. Where we have a place where the motorcycle is not moving at all, then we have 0. And if the slope is 0, then acceleration is also 0. And the negative slope, that is decreasing. It'd be negative and negative again. It's not a very graceful stop when he gets to the end, maybe. Good. Practice problems from 2.3 that you should be able to do will be number 1 through 14. Page 107. Number 1 through 14. Practice problems.